Good afternoon, everyone. So first, I would like to thank the organizing committee for inviting me to be a speaker. It's a pleasure to take part of this first automatic control meeting, promoting our community and also celebrating 20 years of the Pell graduating program and 75 years of WERJ. So my talk is about backstepping methods for analysis, control, and observation of thermoacoustic Rijke tube dynamics. So this is a very challenging problem. And it's very simple to reproduce in any lab, in any university. It's a very cheap setup to buy and to study control strategies. But its dynamics is very complicated. So it's a very rich system. And I have some interesting results here that I would like to share. So first, the Rijke tube was invented in the 1800s by a physicist, a Dutch physicist, Peter Rijke. And he noticed a way to generate sustainable oscillations in a vertical open tube using only heat. So this phenomenon was called thermoacoustic instability. And there are a lot of engineering examples that this kind of instability happens, and they need to be mitigated. And one way to mitigate this kind of instabilities are using feedback. So basically, the Rijke tube, this is a modern Rijke tube because we added sensor and an actuator. So we have a vertical tube open at both ends and a heating element, usually in the lower half of the tube. So the phenomenon is the following. When we hit this heating element, the air inside the tube gets light, so the air gets sucked in the tube, and the pressure inside the tube increases. So it increases until a point the air is expelled, and then the cycle repeats, generating a limit cycle behavior for the acoustic pressure. Okay? So we added a microphone at this boundary to measure the pressure, and a speaker in the lower half to use it as an actuator. So the idea is to add some perturbation, acoustic perturbation at the bottom to stabilize the pressure field inside the tube. Okay. So this is a visual of the acoustic instability inside the tube. So when we hit the heating element, the pressure starts to grow exponentially until saturation. So we have this limit cycle behavior, which is non-symmetrical, as can be seen here. And due to the frequency of this oscillation, we can hear this this instability because the pressure oscillates in an audible frequency. So it's interesting to see in practice how it works. Okay. So we want to mitigate this kind of behavior using feedback. This kind of phenomenon, as I said before, appears in several engineering systems, such as gas turbines, industrial burner, combustion chambers. And due to the oscillations they generate, they can damage the system. So we have always to try to mitigate this, this phenomenon. And usually, when the system has its best performance is in this unstable operating point. Okay, so the control in this kind of system is mandatory. Okay. But the problem to study thermoacoustic instability in this kind of systems is the combustion process, because we have chemical reactions which are very highly nonlinear and not fully known. Okay, so the Rijke tube eliminates the combustion process by adding this heating dynamics. And still, it can reproduce what happens in practice in this kind of engineering applications. Okay, so my talk will be based on some recent papers I have published with my collaborators. So until today, there is no other results in literature using an infinite dimensional approach. So the backstepping methodology was the only control strategy we found in the literature that was able to stabilize the system. Okay. Also, we developed state estimators for this phenomenon, which are interesting in practice for monitoring the instabilities and to estimate the pressure field, okay, inside domain. Okay, so first, the mathematical model of the Rijke tube. So we have two kinds of physics. We have the acoustic dynamics and the heating release dynamics. They are coupled by the velocity at one point of the domain. So this is the reason why we have in the right-hand side of the pressure, acoustic pressure dynamics, this delta function is to couple the heating release at the point x0. And also we have the acoustic velocity inside the tube. Okay, so these two equations are well posed by including the boundary conditions, which represent the open tube. So basically, we have at the bottom boundary the relation between pressure and the velocity and the actuator, and at the upper boundary we have only the relation between pressure and velocity. Okay? This term Z0 and ZL represents some dissipation, the acoustic dissipation in the system. Okay, and the heat release dynamics is basically a first order ODE, which depends only on the velocity, so it's a linear ODE. Okay. So this system is forms a hyperbolic PDE. So hyperbolic partial differential equations are notorious difficult because they usually model transport. So basically we have several delays. Okay, so here we have delays depending on the state. But for these systems we have the so-called characteristic coordinates, which is a transformation that transform the physical coordinates into these characteristic coordinates that represent the system into transport equations. So we lose the physical interpretation of the equations, but we gain insights about the stability of the system because transport equations are simple to analyze, to understand. Okay, so our states after this transformation will be a linear combination of pressure and velocity. Okay, so using this transformation, our system is rewritten this form. So we have two transport PDEs, one propagating from the left to the right, and the other from right to the left. And both have a discontinuous point at x equal x0, okay, due to the heat release. Okay. So we have this diagram that helps to understand what's happening in these coordinates. So basically we have both states, R1 and R2. So we are transporting the information from this boundary to the other boundary, the top of the tube. And this information is constant along the domain. But at this point where we have this heat release dynamics, there is a discontinuity. So the value of the state at this point is increased by this quantity here. And then passing the heating point, the information propagates along the domain constant and is reflected at the boundary to the other state. And the same behavior we have here. The information is transported without dissipation along the domain. And at this point, we have a gain due to the heat release dynamics. And after that, this state keeps constant and is transported along the domain. And we have this cycle here, this internal feedback inside the system. So we can see here that depending on the size of the gains, this internal feedback of the system makes the states grow, and then explaining the unstable behavior. Okay? But okay, although we have gain insights about the instability of the system, what is happening in this system, this is still difficult to tackle as a control problem because we have a discontinuous right-hand side in these equations. So we will do one more step, one more transformation, which we called a folding transformation. So basically, what we are gonna do is to create artificial states. So we have the information being transported, and here we have the discontinuous point, x0, and the coupling between the variables. So this is R1 and this is R2. So we create two more states, which we will call, we will recall R1 as alpha 1 and beta 2 if x is in the lower half of the tube. And in the second half, we call beta 2 because this will be alpha 1 and beta 2, but then we will have alpha 1 here, and this piece of the domain will be a new one. Okay, so we couple both intervals by boundary conditions, and then we are able to remove the discontinuity from the domain. We added a discontinuity in the boundary condition, but it's no problem. This is already solved in the literature. And we do the same for the state R2. So we will have more states, more boundary conditions, but now everything is continuous, okay? And we also, for simplicity, rescale the domain for everything evolved from 0 to 1 instead of 0 to L, the size of the tube, okay? So in the end, we need to stabilize these dynamics. Now we can see that we don't have more discontinuities in the right-hand side, but we have much more states, much more boundary conditions, and the coupling between the PDEs and the ODE happens in the boundary. Okay, so, but this is no problem to be solved. Okay. So this is our framework to be stabilized. Okay. Okay. One important information we gain using this framework is we can see that this system is a non-strict feedback form, okay? Because we see that now the boundary conditions, the coupling between the boundaries are a mess somehow, because we can see that the states propagates from 0 to 1 in this direction. Then there is a coupling between the state and the ODE at the boundary condition. And this boundary condition is coupled with another PDE that is again coupled with the first one. So there is a feedback loop here. And also here there is another feedback loop. Okay? So the system cannot be put in a triangular form. So this is another difficulty to be solved. Okay, so how we solved this problem? So we use the backstepping method for partial differential equations. The backstepping method is what we call the constructive method to design control laws that achieve Lyapunov stability. So instead of do eigenvalue placement, as we do in classic control, here we propose a target system, a desired closed loop system we want to get. And we have a transformation. We have to find the transformation that makes the original system, this unstable one, to the target system, which is the stable one. Okay, so it's not a strategy that fits all problems, because it requires the knowledge of the designer to see what's possible, what terms can be cancelled by the feedback law and which one cannot be cancelled. And doing this, we have to try to find this transformation that makes the system stable, okay? So basically, backstepping has 4 steps. The first one is to identify the undesirable terms of the PDE. We saw that in our case, the undesirable terms is the coupling between the PDE and ODE, because we have that feedback between the states. And then we have to choose a target system which removes the undesirable terms that make the system unstable. Find the state transformation that makes this unstable system be mapped to the stable one. And then find the boundary feedback or the observer gains from the transformation, okay? So in our case, our target system will be this one. So this system, we can see analyzing this diagram that it's exponentially stable. So starting from this state here, which is have boundary condition equals 0. So this information 0 is propagated through the domain until the upper boundary. So this state will be 0 in finite time. And then the value of the state at this boundary will be the input of this in this ODE. So this term will be equal 0 in finite time. Okay, after this information 0 is transported to the top here. then this term becomes equal 0. Then this information equal 0 is reflected to the other state, transported. So this other state here will be 0 in finite time too. And this cascade structure makes these states becoming 0 in finite time in a cascade form. So this other term, alpha 2, will be 0 in finite time. And then when this term, when this state is equal 0, both of these terms are already 0. So we will have an exponentially stable ODE here. And then, so this state is going to 0, so it will be input to state stable, okay? So basically, we only removed some couplings between the ODE and this state, and between this state and this other one, okay? So this is our desired closed loop system. Now we have to find the control law that makes this happen. Okay? So to find, okay, so first we need to know what we are intended to say about stability. Since we are working in infinite dimensional spaces, the concept of stability is different. There is no equivalence between the norms in infinite dimensional spaces. So here, what we called exponential stability is in the L2 sense. So if I have L2 initial conditions, and for the OD it doesn't matter, I only need to have a real value, then the system is stable if this inequality is satisfied, okay, for all t greater or equal 0. Okay? So we can prove mathematically that the target system I showed in the previous slide is exponentially stable in this norm. Okay, so this is good because now I have a Lyapunov argument to show that this system is stable in the sense of this norm. Okay, L2 Cartesian R. Okay. So to get the feedback controller, we propose this transformation, which is the Volterra transformation. So I have the state that I want to transform, alpha 1, alpha 2, beta 2, and the state Q. And the new state, psi 1. So I have these terms, phi, k, g, h, that need to be found in order to map the original system into the target system. Okay, so the problem here is to find what is the equations of these kernels here that make the mapping feasible. Okay. So these kernels, K, G, H, evolve in different domains. For example, the kernel K, which is the kernel of Volterra transformation, has a triangular domain. And the kernel J and H, which are the kernels of Fredholm transformation, are lie in a square domain. Okay. Because of the intervals of the integrals here. Okay? And phi is a finite dimensional kernel, which is easier. Okay? So to find the equations of the kernels, we have to substitute this transformation into the original system and see how the kernels have to be in order to cancel the undesirable terms and get the target system. So in the end, we will have the target system if and only if the kernels satisfy these PDEs and this ODE together with the boundary conditions here, okay? So if I am able to solve these equations, I can find a control law to solve the problem. So But this is possible. Actually, we proved that these equations have a unique solution, which are bounded. They are not continuous, but they are bounded. There is no problem about that. And to show that this transformation, these kernels have a unique solution, we basically have to solve these PDEs and this ODE using the method of characteristics. So the method of characteristic, basically you transform the PDE into an ODE and integrate along the curve. Okay, so for the kernel K, we have a explicit solution, which is given by this expression. So we can see that basically we have a boundary condition here in this triangular domain, and the information propagates with no dissipation, and given by this expression. Okay. Similarly, we can find a solution for the kernel G, which will be giving this expression. Here we have a much more complex equation because we are in a square domain. We have two boundary conditions here. Okay. And for the kernel H, similarly, we can solve using the method of characteristics, and we obtain the explicit solution. Okay. And finally, the ODE, which you can see in the end, the solution of all the other kernels depend on the ODE of phi. As you can see here, K depends on phi and H, but if you see here, H depends on phi. So in the end, the solution of K depends only on phi. This, similarly to J, the solution is 0 in interval and equal to phi in another interval. So in the end, everything boils down to solve the equation for phi. So if phi has a solution, the problem is solved. Okay? So if you take a look at the ODE of phi, we have this expression, so it depends on H. But if we take a look in the structure of H, we can see that H is 0 if this inequality is satisfied, and depends on phi if this inequality is not satisfied. Okay, so we can break the problem in two cases. If the parameter lambda 1 is bigger or equal than lambda 2, we have that H is equal to 0 for all values of z between 0 and 1, which means that this term vanishes. So this ODE, in the end, is this, can be rewritten to this one, which is easy to solve, and the solution is this expression. Okay? So for this case, the problem is solved. If this is not the case, then we have to solve the problem iteratively. So if lambda 1 is strictly smaller than lambda 2, then we have to solve phi backwards, which means we analyze the interval where h is equal 0, which will be for this interval here. So the ODE of phi doesn't depend on h because it is equal 0. Then we can solve it in this interval, get the solution, and move to the next interval. So in the next interval, which will be this one, we substitute the solution of h in the equation, but the solution of h, as we can see here, depends on phi in the interval we already solved. So we can do this procedure in intervals of this size and finding the solution of phi iteratively using this process, okay? And of course, coupling the pieces between these intervals. Okay, so doing this, we are able to solve the equation from 0 to 1, getting all the solution. And the interesting point is what physically means lambda 1 be smaller than lambda 2. If we substitute the expression of lambda 1 and lambda 2, we can see that when lambda 1 is small, it means that the heating element dynamics is close to the upper boundary. So this means that if the heating element is much closer to the upper boundary that the controlled boundary, the bottom, the problem is more difficult to solve because we have to break the problem of solving 5 in several pieces, okay? But if this is not the case, it means that the heating element is closer to the actuated boundary, so the problem becomes easier to solve. Okay. So the last point in our control strategy is to show that the transformation is invertible. If it is invertible, it means that the spaces I'm working with, they have the same topological properties. So if I'm working in this transformed system that is exponentially going to 0, it means that in the original coordinates, this state is also going to 0. But we can always show that the transformation is invertible if we rewrite this transformation in this form and using some results of functional analysis in integral equations. So if we have the kernel of the integral here bounded, which means that the solution is in the supremum norm is not infinity, then this integral operator is bounded in L2, and the operator I minus t is invertible in the space L2, and this equation admits an unique solution. So we have the invertibility property, okay? So it means that if I'm mapping 0 in the transformed system, I'm mapping 0 in the original system too. Okay. So with this, we get the theorem of closed loop stability. So our control law will be this one. So we have the states in the control law and the integrals of the state multiplied by the kernel. So it's a static feedback law, okay? And for any initial condition in L2 and Q in R, we get that the zero equilibrium is exponentially stable in L2 Cartesian R, okay? Which means that the states are decreasing, satisfying this inequality here, okay? So this is the visuals of the kernels. In the case 1, when lambda 1 is bigger than lambda 2, which means that the heating element is in the lower half of the tube. So we can see here that the kernel H is equal 0. The kernel K is continuous, and we have a triangular domain here where the values are evolving, and the kernel J is discontinuous but is bounded, okay? And the kernel phi is continuous, okay, actually C1. So in the second case, where it's much more difficult to solve, then we have all the infinite dimensional kernels with a discontinuous behavior. And phi is still continuous, okay? But there is no, it's C0 continuous, okay? Okay, and when I implement the feedback law in the system, this is the evolution of the states. So we have the the pressure here in the lower half of the tube a long time. So the pressure is going to 0. The velocity in the lower half of the tube is going to 0. And also the pressure in the upper half of the tube going to 0. And the same for the velocity, okay? And also for the second case, we also get the exponential stability. Okay? All the states are going to 0 exponentially. Okay, so the big problem of this control law is that we need full state measurement, which means that we have to have sensor along all the domain in order to apply the control law, because the integral goes from 0 to 1 and depends on state, okay? So there is no way I can implement this control law in practice, because I have to include a huge amount of sensors in the domain, okay? But we can develop a state observer in order to estimate these states along the domain, based only in a sensor, pressure sensor installed in the boundary condition of the system. And this is our next step. So we also developed a backstepping state observer, which is basically a Leuenberg observer. We have a copy of the system, and we add the output injection terms in the right-hand side. So in order to estimate the states, we have to find the observer gains here, multiplying the output injection terms, that makes the aerodynamics stable, okay? And this is our the value of the pressure, okay, in characteristic coordinates in the boundary condition. It's given by this expression here, okay? So if we define the aerodynamics, we find this dynamic that must be stabilized by the observer gains. So basically, the aerodynamics is open loop unstable, because basically, since this is a copy of the system and the system is open loop unstable, then the aerodynamics is unstable. So we have to stabilize by designing these gains here. So the idea is the same as the control method. So we have to design a target system that we want to map the aerodynamics. So we chose this target system, which was motivated by the control problem. It's the same idea, to remove some couplings between the states and to inject 0 at one boundary. So the cascade structure of the system will make it goes to 0 exponentially, okay? Okay, the transformation, the same idea as before. We have a backstepping transformation with Fred-Hall terms, because they have integrals from 0 to 1, and the Volterra term, which is from 0 to z. The Volterra term is mandatory to have, because it is the term that makes the transformation invertible. Without it, the backstepping transformation is not invertible, so we don't have the topological properties preserved when we apply the transformation, okay? So the steps are the same as before. We differentiate the transformation, substitute the dynamics of the system, and see how the kernels of the transformation have to be in order to cancel the undesirable terms and make the system stable. So in the end, we will get these kernels, which are essentially the same as the control problem, because in backstepping, the observer design is the dual problem of the control problem design. And we can show using the method of characteristics, as I showed before, that this set of PDEs have a unique solution bounded in the supremum norm, okay? Okay, so doing this, we'll get the explicit solution of the observer gains, which will be this one. They depend on the solution of the kernels at one point, at one boundary, okay? So the advantage here is that we obtain a explicit form of the gains, okay? We do not need to solve in real time every iteration an equation to get the values of the gains, okay? Since we have the analytic solution. And then, putting all these pieces together, we have the stability of the observer proposed with the gains given by this expression will guarantee that the estimates of the state using only a pressure sensor at the upper boundary of the system will converge to the real ones in the L2 Cartesian R sense, okay? So this is the idea of the, this is the visuals of the kernels. So they are very similar to the other ones I showed before. They are discontinuous. And for the easier case where one of the kernels is equal 0. And then we have here the aerodynamics of the system. So we have that the estimated states are converging exponentially to the real one, so the error is going to 0 everywhere, okay? You know, values. Okay, so we have designed the backstepping feedback controller, which is a full state feedback controller, and we have designed a backstepping observer design that only needs the value of the pressure at the one boundary. And since the system is linear, we can apply the separation principle, that is the combination of the designs which were made separately, produces an output feedback controller that stabilizes the system. So this is the final result I would like to show. So if we have this signal available at the upper boundary, then the control law, which is computed using the estimates of the states instead of the real ones, will make the system stable in the L2 norm. Okay. Okay. Okay, that's it. Thank you for your attention.